Hello, I am Mrs. Edwards, and it is time to do math, and I love it. Today we get to graph some logarithms using a variety of techniques, and as we graph, we're going to start seeing some features that are in common to all logarithmic graphs. So let's get started. Anytime you have really no idea what the graph of something looks like, it's a good idea to maybe plot a couple of points. And if we're going to plot some points, we need to know what numbers are we allowed to substitute in for x so that when we get an answer y, we can plot that point. So what I've done here is I've just simply jotted down the logarithm of several different x values. Let's take a look at what happens when I try to take the log of 5. So the log of 5 has an answer of about 0.7. The log of -2 is an error message in a calculator. It's undefined. Okay, here are a few more. Okay, so what I want you to notice is that it seems we cannot take the logarithm of a negative number, and we also cannot take the log of 0, which means the domain, the inputs there, are just positive numbers. So not including 0 through infinity is what we can take the log of. Now, why is that? I'm going to try to quickly explain to you why that is by just rewriting this equation of a logarithm in a form that's a little more familiar. If we change from log form to exponential form, the equation we get is equivalent to this one, just in a form, again, that you're a little more familiar with. We went over changing from log form to exponential form in the last lesson, and I use the beaver method here that I made up. When we don't see the base, we know the base, first of all, is 10, and that beaver tunnels under. Okay, that base number tunnels under, comes up under the other side, pushes that up, and the log falls in the hole. Now, that's a quick reminder for those of you that watched my previous lesson. Otherwise, you're like, what in the world are you talking about? Okay, but all of that is to say that that original equation, y equals log of x, is equivalent to x equals 10 to the power of y. Now, why can't you take the log of 0 or a negative number? Well, you just try thinking of a y value. Think about plugging in numbers there for y. Think of all the numbers that could go in there. Positive numbers, negative numbers, 0. Plug anything you want in for y. And what will the answer be? Well, if you pick 2, 10 squared is 100. I pick 3, I get 1,000. We're trying to make the answer negative. Can we do it? What if I do 10 to the -1? That's 1/10. What if I do 10 to the -2? I have 1 over 100. 10 to the 0 power, I get just 1. No matter what number I substitute in for y, which is the answer to the logarithm, no matter what number I plug in for y, I'm only going to get out positive numbers. It's impossible to get out a negative number or to get out 0. That is why we cannot take the log of 0 or a negative number, because x really represents the answer to an exponential function, which is going to be greater than 0. Because this video is going to get very long, I want to cut to the chase on a few of these points. So let's say I go and I plot a handful of points. The reality is, since you can't take the log of 0 or a negative number, there's going to be a barrier there. We won't have any graph there to the left of the y-axis, since we can't substitute negative numbers or 0. And then there's a log property here that if I do substitute 1 in for x, it is good for you to know the log, no matter what the base is. This one happens to be base 10. But let's say we have the natural log of x, the log base 4 of x, the log base 17 of x. No matter what the base is, when you take the log of 1, you get out 0. Okay, so just plotting that point. And if you plotted a number of points, the graph of the logarithm is going to look like that. And all logarithms have that basic shape. Okay, they get really, really close to a vertical asymptote, and then they climb oh so very slowly. I'll get there when I get there. Okay, so logarithms like the lazy logs. And then a warning, if you are graphing using a graphing calculator, the graph of the logarithm, it makes it look like it stops. Okay, like a square root graph starts and then it curves on over. And it does not stop in a logarithm. Okay, it goes down forever, getting closer and closer to that vertical asymptote. But again, a warning on a graphing calculator, it makes it look like it stops even though it does not. All right, so climbing very slowly. This is basically our parent function for a logarithm. All the logarithms look like this. Now let's do a little quick comparison to see where the graph of a logarithm comes from. The graph of 10 to the x, right, the J curve, an exponential function, it turns out that the graph of a logarithm is just a reflection of an exponential function. Let's just highlight a handful of features. Okay, so the coordinate on the log is 1, 0, and inverses, right? The x's and y's flip-flop. So if we have a coordinate 1, 0 on the inverse, it would be 0, 1. Well, everything about a log function is a flip-flop of the exponential function. So if they are inverses, okay, and a log function has a vertical asymptote that's the y-axis, well, if everything's flip-flopped, right, that is why for an exponential function, it's the x-axis that is the asymptote. Let's go ahead and continue on, finding a few other features. Okay, is the graph continuous? Can you draw this graph without lifting your pencil? That's really what continuity means. So yes. Now a little bit more specific over its domain. Since the graph is not anywhere to the left of, in this case, -2, there's no function there, so there's no place to draw. But over its domain just means from -2 through infinity, could you draw this without picking up your pencil? So all log functions are always continuous. Bounded. There are not, you can't find a logarithm that is bounded, okay? None of them are bounded. This graph goes forever up and forever down. We can't put a floor and a ceiling that will contain the function. So not bounded. Increasing, decreasing. Log functions are either all increasing or all decreasing depending on how we shifted these around or reflected. This particular one, as I move my eyes from left to right, as I jump on that curve, see how my eyes go up, 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 up forever. This one is all increasing. Okay, so they're either going to be all increasing or all decreasing. Fancy word for that is monotonic. Okay, then extrema. Okay, remember back, what does extrema mean? Those are local mins and maxes. Like a parabola might have a minimum or a maximum. Okay, logarithms do not have local mins and maxes because the official definition of a local minimum, for example, is the point where a function changes from decreasing to increasing, right? I go downhill and then I go uphill, and that is where we have a min. Or I'm going uphill and then downhill, and that's where we have a max. So we're not changing from increasing to decreasing or decreasing to increasing, so we can't have any local mins or maxes. So logarithms do not have local mins or maxes. They will not have any extrema. Okay, end behavior. We only talk about one side. Okay, because logarithms, they're either going to be moving to the right or to the left, depending on how you've moved it around. So since this one is moving to the right, we're going to find the limit as x approaches infinity, meaning we're plugging in x values 1, 2, 3, 4, 5, 6, 7, forever to the right into the function. And we're like, what's the pattern? What's happening to the answers? Well, if I substitute in, say, -1, I get out 0. If I substitute 1, I get a height of 1. If I substitute in 1, I have something a little more than 1. Okay, I substitute in 2, and I end up with a height of 2. As I continue substituting numbers in, getting bigger, 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 the y-coordinates are going to get higher, higher, higher. I know it's very slow, but it's going up forever. So the height of the function is going up, up, up. It's heading to infinity. Okay, so end behavior. So a review of those topics. So now that we have, looked at some of the features of the functions, let's try to put this all together to graph this function. We want to, before we get graphing, let's find the domain. So think about, what do you do to find the domain? If you want to find it really quickly, it's the numbers that you're allowed to substitute in, and you get a real number answer. Well, we can only take the logarithm of positive numbers, and we're going to be taking the log of whatever the answer is to x plus 6. So you want to set that argument, x plus 6, greater than 0. Then subtract 6, and our x's need to be bigger than -6. If we use interval notation, that is parenthesis -6 through infinity. The range of every logarithm, even though they climb so very slowly, it's forever up and forever down. So the domain is all real numbers. Vertical asymptote, just simply set the argument equal to 0 and solve. Okay, so subtract 6, and our vertical asymptote is at x equals -6. Now, just with that little bit of information, you could make probably a rough sketch of this logarithm. But let's go ahead and do a bit better than that using, again, those transformations. Okay, parent function. What's the parent function for this one? That would be log of x. In this particular one, the base number is 10 since we don't see it. Okay, log base 10 of x. So what do all basic log functions look like? Okay, they have that vertical asymptote, that's the y-axis. They go through the coordinate 1, 0 because the log of 1, the log, no matter what the base is, of 1 equals 0. And then they move to the right, up, up, up very slowly, and then they draw closer and closer to the y-axis. Okay, we've got our basic shape. Now, transformations, a review. So I'm rewriting that to try to make each piece stand out. The -2 out front really means -1 times 2, so those are separate. The order that you transform something matters. So the story is you wake up in the morning and you stretches first. Then before you walk out the door, you check your reflection. Reflections next. Make sure there's no toothpaste. Okay, then you move about your day. Up, down, right, left. So it doesn't matter if you do right, left, or up, down, whichever one you want to do first is fine. Okay, so starting with wake up in the morning and stretch. So times 2, that is a vertical stretch by a factor of 2. Multiply by -1. multiply, kind of a visual there, right? Multiply by -1 is a reflection across the x-axis. Add 6 inside of grouping symbols. That's going to move us left 6. And then the -7 outside of grouping symbols is down 7. All right, I'm going to go ahead and make that sketch. Okay, running through that one more time. All right, so we're starting off with our parent function, y equals the log of x, with the y-axis being the asymptote. Okay, then moving to the times 2 is a vertical stretch. So notice we are further off the x-axis. We're twice as high, but it does not change when you do this. It doesn't change the location of that asymptote. Then multiply by -1, reflected across the x-axis. It did not change the location of the asymptote. Okay, then adding 6, we're going to drag everything left 6, and that does change the location of the asymptote. So instead of being the y-axis, it's now back at -6. And so now we next want to grab everything here and drag it down 7. And there is our final graph of log, -2 log of x plus 6 minus 7. Okay, there's our final graph. Okay, how about another one? What happens if you replace the x with a -x? Okay, let's start with the parent function. Okay, the parent function for natural log of x. It simply means the base is e, 2.7. So it's still going to look like that basic log function. And then the only thing that's been done to it, x, was replaced with a -x, which is a reflection across the y-axis. All right, so here's a quick picture of that happening. So I'm graphing that basic logarithm look, right, through the coordinate 1, 0. Y-axis is my asymptote, and then grab it and reflect it across the y-axis. That does not change that vertical asymptote. So that orange one there, that is the graph of y equals natural log of -x. Let's sketch another to make sure you've got these transformations down. The parent function for this one would be log base 4 of x. If I draw that in, right, the basic shape of all logarithms, y-axis is the asymptote. We have an x-intercept at 1, 0, because the log base 4 of 1, the log of any base of 1 is equal to 0. And then it curves over, growing very, very slowly, but going forever up and then going down. Okay, so there's my basic look. Transformations. We wake up in the morning and we stretch. We want to do stretches and compressions first. That multiply by 1/2. That is a vertical compression. We're going to squish it this way by a factor of 2. Okay, then before we walk out the door, we check our reflections next. And this -1 times x, when you have it inside of grouping symbols, x was replaced with -x. So that means that we reflect it across the y-axis. Okay, then the adding 5 inside grouping symbols. This is the tricky one, okay, because normally when you are adding inside of grouping symbols, it shifts it left, right? The opposite kind of what we think. But whenever you have a -x inside of grouping symbols, then it does the opposite. So it is going to move it right 5. Let's look at that in action. Okay, I'm going to sketch in that basic logarithm, log base 4 of x, with an asymptote that's the y-axis. Next, I'm going to compress it by a factor of 2. So see how it's squished? The heights were half as tall as they used to be. Reflect across the y-axis, still not changing the location of the asymptote. Okay, and then lastly, we're going to drag everything to the right 5, and that means the asymptote 2. So the asymptote is now at positive 5, and there is the final graph of 1/2 log base 4 of negative x plus 5. If I simply wanted the domain, I would set negative x plus 5 greater than 0 and solve. If you do multiply or divide by a negative number, remember to flip that inequality symbol over. And then if I wanted the equation of this asymptote without doing all the movements, I could just set negative x plus 5 equal to 0 and solve, and you would end up getting 5. Okay, so we have our x equals 5. One thing that I have talked about, or I guess alluded to, we were talking about parent functions, and I have not worried about the base at all. And that is because if you had an exponential function, 2 to the x, 3 to the x, 4 to the x, when those base numbers are greater than 1, we just get that J curve, and yes, 2 to the x versus 10 to the x. It's just that the 10 to the x swoops up a little bit faster. Well, it's the reverse is true when it comes to logarithms. If you were to graph the log of x, okay, that's base 10, notice that basic look. I do the natural log of x, you can barely tell a difference, and that's because it's climbing so slowly. I thought it was worth showing you on Desmos, if you have a base other than base 10 or the natural log, you've got to come over here to the functions, and then in the functions miscellaneous, you can select the logarithm that allows you to input any base that you want. Now, that's just a calculator trick, okay, but ultimately when you sketch these graphs, you're not really going to pay much attention to the base number, frankly, because it's not going to affect the shape or really hardly even the location, because it takes an enormous x value just to get to a height of 4. So there's a marginal difference. Okay, so you should be able to find the domain by setting whatever you're taking the log of, what's inside parentheses greater than 0 and solving. What's inside parentheses equal to 0 gives you your vertical asymptote. And then you can use your transformation rules to move it around. Property, right? The log, no matter what base of the number 1 equals 0. That's because of the inverse functions, because a number to the 0 equals 1. So the log of 1 equals 0. Okay, so you've got a lot to take away with these logarithms. So I guess get going. Good luck.